Good morning, students. In today's lecture, we will continue the problems related to stability of floating bodies. So our first problem is a homogeneous circular cylinder of specific gravity S floats in water with its axis vertical, and the radius of the cylinder is 2/3 of its height. We are to show that equilibrium cannot be stable if the specific gravity of the cylinder lies between 1/3 and 2/3. It means we are to prove that if the equilibrium is stable, either the value of S is less than 1/3 or it is greater than 2/3. Now to prove this, let us consider this represents a homogeneous circular cylinder having the specific gravity S. The cylinder is floating in water. This line is a vertical line which is axis of the cylinder, and the radius of the cylinder that is given to be 2/3 of the height. Let us take h is the height of the cylinder. So according to the question, the radius is 2/3 of this height h. Let us take length of the axis immersed, means this length. This we have denoted by h dash. G we have taken as center of gravity of the cylinder. H, that is the center of gravity of the immersed part of the cylinder. M, we have denoted the position of metacenter. So first of all, let us find the length HM. To find HM, we will have to find the volume of this part and the moment of inertia of plane of flotation. Here, the plane of flotation is this plane, which is a circle having the radius, suppose the radius is A. Now, volume of the immersed part of the cylinder. By the formula of volume, this is given by pi into radius square into the height. Radius of the cylinder is A, so volume will be pi A square into the height of immersed part of the cylinder is h dash. So the volume will be pi A square h dash. Now the moment of inertia of the plane of flotation about the diameter, that is given by A into k square. A is the area of the circle, k is the radius of gyration. Area is pi into radius square. Radius is A, so area will be pi A square. And k square is A square by 4. Now substituting the values, we get HM is equal to AK square upon V. AK square is pi A raised to the power 4 upon 4. And the volume of the immersed part, that is pi A square h dash. So from here, we get the length HM, which is given by A square upon 4 h dash. Now, in the next step, let us find this length HG. Now HG is OG minus OH. OG, G is the center of gravity of the cylinder, and therefore OG will be the total height of the cylinder divided by 2. Total length of the cylinder is h, so OG will be h by 2. And OH, H is the center of buoyancy, means center of gravity of immersed part, so that will be at the height, total height of this part divided by 2. So OH will be h dash by 2, and therefore HG, that is given by h by 2 minus h dash by 2. Now let us apply the condition of stability for the equilibrium. Now equilibrium is stable if the metacenter lies above the center of gravity. It means HM is greater than HG. HM we have obtained a square upon 4h dash, and hg is h by 2 minus h dash by 2. So from here we get a square is greater than 2h dash into h minus h dash. Now in the next step, let us apply the condition of equilibrium. Means weight of the cylinder is equal to weight of the liquid displaced. Weight of the cylinder means volume of the cylinder into density of the cylinder into G. Let us take density of the cylinder is rho. So the weight will be pi a square h into rho into G. Now to find weight of the water displaced, volume of immersed part of the cylinder into the density of water into G. So the weight of water displaced is given by pi a square h dash rho dash G. Now from both sides the same terms will be cancelled out. So pi a square G is cancelled out. So we get h rho is equal to h dash rho dash. Now from here we get the ratio of rho and rho dash, which is given by h dash upon h. Now rho is the density of cylinder, rho dash is the density of water. Density of cylinder divided by the density of standard substance, that gives us the specific gravity of the cylinder. So the specific gravity of the cylinder is equal to h dash upon h. Specific gravity of cylinder is given to be small s. So we get s is equal to h dash upon h. From here we can find the value of h dash, which is given by s into h. Now from here equilibrium is stable if a square is greater than 2h dash into h minus h dash. Here substituting the value of a and h dash. The value of a is 2 by 3h and the value of h dash is s into h. So putting the values here, we get 2 by 3h whole square is greater than 2sh into h minus hs. Simplifying this expression, we get 9s square minus 9s plus 2 greater than 0. Now we can factorize this expression to get 9 into s minus 1 by 3 into s minus 2 by 3 is greater than 0. Now product of these two factors is positive. So either both factors will be positive or both will be negative. So in the first case, if both factors are positive, then we get s is greater than 1 by 3 and s is greater than 2 by 3. So from here we can say that s will be greater than 2 by 3, because if s is greater than 2 by 3, then it is also greater than 1 by 3. In the second case, when both of these factors are negative, we get s is less than 1 by 3 and s is less than 2 by 3. So from here we can consider s less than 1 by 3, because if s is less than 1 by 3, then it will also be less than 2 by 3. So we have proved if the equilibrium is stable, either s is less than 1 by 3 or s is greater than 2 by 3. It means the equilibrium is not stable if s lies between 1 by 3 and 2 by 3. So this completes the solution of this problem. Now our next problem is a cone of specific gravity s having the height h and the radius of whose base is r floats in a liquid of specific gravity capital S with the axis vertical and vertex upwards. We have to prove that equilibrium is stable if h square upon r square plus h square is less than cube root of s minus small s divided by s. This capital S is the specific gravity of the liquid and this small s is the specific gravity of the cone. So to prove this expression, let us consider a cone having the height as h and the radius of the base is r. This cone floats in a liquid. The specific gravity of the liquid is capital S. Let us take OC is the axis of the cone. O is the vertex here, which is upwards. Now, let us take H dash is the height of the axis, which is outside the liquid, means this length is H dash. This is the plane of flotation, which is a circle, and the radius of this circle is this length, which we can find from this triangle. This is a right angle triangle. If we consider the semi-vertical angle as alpha, then perpendicular upon base is equal to tangent alpha, and this length is h dash. So the radius of this plane of flotation will be h dash tangent alpha. Now to find hm, h is the center of buoyancy, means center of gravity of immersed part of the cone. Here the immersed part of the cone is this frustum. G is the center of gravity of the cone. M is the position of metacenter. Now to find hm, let us find the volume of immersed part, means volume of frustum. To find the volume of frustum, you can directly use the formula for the volume of frustum, or either you can find the volume of this cone and subtract it from the volume of larger cone. Then you can find the volume of this frustum. So here, to find the volume of frustum, let us subtract the volume of this cone from the volume of larger cone. Now the volume of larger cone, that is 1 by 3 pi r square h, because r is the radius of larger cone and the height of larger cone we have denoted by h. For the smaller cone, the radius is h dash tangent alpha and the height is h dash. Now the value of radius of larger cone, that is BC, that can be obtained from the right angle triangle OCB. In the right angle triangle OCB, BC upon OC means R upon H is equal to tangent alpha. So the radius will be H tangent alpha, which is the radius of the larger cone. So putting the values here, we get the volume of the frustum, which is given by 1 by 3 pi tangent square alpha into h cube minus h dash cube. Now let us find the moment of inertia of this plane of flotation about this diameter. By the formula, it is given by area into the square of radius of gyration. Area is given by pi into square of radius. The radius of this circle is h dash tangent alpha, and value of k square is square of radius divided by 4. So putting the values, we get moment of inertia of plane of flotation, which is given by 1 by 4 pi h dash raised to the power 4 into tangent alpha raised to the power 4. Now let us find hm. By the formula, it is given by a k square upon v. V is the volume of the immersed part of the cone. So both of these we have obtained already. Substituting their values, we get the length hm. This completes our first step. Now in the second step, let us find the length hg. To find hg, we require cg and ch. Cg is the height of center of gravity of the cone above the base, and ch is the height of center of buoyancy above the base. Now cg is given by 1/4 of total height of the cone. Total height of the cone is h. So cg will become h by 4. Now to find the height of h above the base, we cannot directly find it, so we will have to use the formula. According to this formula, if we have a compound body consisting of two parts, w the weight of the compound body, x bar is the depth of its center of gravity above the base. W1 is the weight of one of the parts of the compound body. X1 bar is the depth of its center of gravity above the base. And then we can find the depth of center of gravity above the base for the second part, which is given by W into X bar minus W1 into X1 bar upon W minus W1. Here, according to our figure, here W is the weight of this cone. W1 is the weight of smaller cone. X bar we have already obtained, which is h by 4. X1 bar will be the depth of center of gravity of this smaller cone from this base. Now let us find the values and substitute here. First of all, weight of the larger cone, which is volume into density into G. Density of the cone, let us denote by rho. So the weight will be volume into density into G. The value of X bar is h by 4. W1 is the weight of smaller cone. Smaller cone weight will be volume into density into G. X1 bar will be the distance of center of gravity of this cone from C. Let us denote the center of gravity of smaller cone is here. Then this distance is h dash by 4 and this distance is h minus h dash. So the distance of this point from here, that will be h minus h dash plus h dash by 4. In the denominator, substituting the values of W and W1, W is the weight of larger cone, W1 is the weight of smaller cone. So from numerator and denominator, we can cancel the terms rho G. And simplifying, we get the distance CH, which is given by h raised to the power 4 minus 4h h dash cube plus 3 times h dash raised to the power 4 upon 4 into h cube minus h dash cube. Now to find hg, hg is given by cg minus ch. Cg and ch both we have obtained, so we can put the values here to get hg. Now in the third step, let us apply the condition of stability. According to condition of stability, hm should be greater than hg, putting the values of hm and hg. And we can see that the denominators are same, so they can be cancelled out. And in the numerators also, we can cancel out the term 3h dash cube. So we get h dash tangent square alpha is greater than h minus h dash. Combining the terms in h dash on the left side, we get h dash into 1 plus tangent square alpha is greater than h. 1 plus tan square alpha is secant square alpha. So h dash into secant square alpha is greater than h. From here we have obtained h dash upon h is greater than cos square alpha. Now we can find the value of cos alpha from this right angle triangle OCB. In this triangle, this is hypotenuse OB. This is R. This length is h. So by Pythagoras theorem, we can find the value of OB, which will be given by square root of R square plus h square. Now we are to find cos alpha. Now cos alpha will be OC upon OB. The value of OC is h. The value of OB is under root R square plus h square. So putting the values, we get the value of cos alpha, which is given by h upon under root R square plus h square. So putting the value of cos alpha here, we get h square upon R square plus h square is less than h dash upon h. Now finally the last step to apply the conditions of equilibrium. According to condition of equilibrium, weight of the body is equal to weight of the liquid displaced. Weight of the body means weight of the cone, and weight of the liquid displaced will be the weight of immersed part of the body. Now weight of the cone, that is volume into density into G. Here in the problem, we are given the specific gravity of the cone as well as liquid. So to find their densities, we can multiply their specific gravities by the density of standard substance. Now the specific gravity of the cone is small s. If we take the density of standard substance as rho dash, then rho dash into small s, that will be the density of the cone. In the same way, the density of the liquid, that will be the specific gravity of the liquid into the density of standard substance, means capital S into rho dash. This is the density of the liquid. Now applying the formulas, weight of the cone means volume of the cone into density of the cone into G. And weight of the liquid displaced means volume of the frustum into the density of the liquid into G. Putting the values and simplifying, we get h cube s is equal to h cube minus h dash cube into capital S. Now from here we can combine the terms with h cube on the left side. So we get h cube into capital S minus small s is equal to h dash cube into capital S. So from here we can find the value of h upon h dash, which is given by the cube root of capital S upon s minus s. This is capital S and this is small s. Now we can substitute this value in the condition of stability of equilibrium, which we already obtained in the equation 1. So here, putting the value of h dash upon h, we get equilibrium is stable if h square upon r square plus h square is less than the cube root of the ratio of capital S minus small s with capital S. Here small s is the specific gravity of cone and capital S, that is the specific gravity of the liquid. So this completes the proof of required result.